So this is just to understand the fraction of people of my age in the audience. Yeah, how many can you recognize? You can. Yeah, you can. Yeah, I know. So thank you very much for being here, and thank you very much to our chairperson and all the staff for the organizing committee. Uh, we in Milan, we organized the first edition after COVID in 23. It was the usual Italian mess. Then in 24 was much better organizing in all modes. And this year we are close to perfection. Thank you very much. And today, since it's the last session of the day and we are tired, I will not go very far. I will stick with the harmonic oscillator. My talk is somehow related to that of Carol before. And so in quantum optics, we use the harmonic model for basically everything. We use for membranes, cavity, particles in the massive version. And of course, we use the harmonic model for the field, for the modes of the field. And today I'm going to deal with the estimation of the frequency. And the idea is to suggest some model to enhance, some strategy to enhance estimation of the frequency. In principle, the job is not very difficult. After all, you solve the Schrödinger equation for the harmonic potential, and you discover that the eigenstates they have some dependence on frequency. So you have your oscillator, you prepare the ground state, and if you are lazy, even just a thermal state, you leave your system to reach the equilibrium. Then you perform some measurement, and from the result of the measurement, you should extract some information about the frequency because the information is there. And you can do that, and the precision is bounded by the celebrated quantum Kramer-Rao bound. So here M is the number of measurements, and Q is the quantum feature information. You calculate the quantum feature information for the eigenstate of the harmonic oscillator or for thermal equilibrium, and you have some result, which is not much encouraging. Can you see you have omega here? And in quantum optics, this can be quite large. So you would need a lot of measurements to achieve a decent precision in estimation. Perhaps some of you say, oh, well, that's complicated. Why not just measuring the energy? After all, the energy of the harmonic oscillator is depending on the frequency. And so I measure the energy, and then I should know the number of quanta. Well, that's very difficult. Measuring the number of quanta of an oscillator is very difficult. Actually, the detectors we are using are working on the opposite assumption. You know the frequency, then you measure the energy, and you reconstruct the number of quanta. So this is not is another strategy which is not viable. So I hope to have convinced you that static measurement, you prepare a state and then you measure something and hope to extract information about the frequency, is not convenient. And so what we can do? Well, we can resort to dynamical strategy. You prepare a state, then you let the state to evolve, and the free Hamiltonian of the harmonic oscillator is encoding information about the frequency. And here, I mean, after you realize this, you understand that time is a resource because the more time you have at disposal, the more information you are encoding, meaning that the tiny difference in frequency are accumulating when you have more time, and so discrimination of different frequency become more easy. And also, energy is a resource. We are used to this in continuous variable quantum information. And to understand intuitively why energy is a resource, think of the picture in the phase space. If a state has large energy, means it's very far from the origin, the bubble of the Wigner function or the Q function. And so when you perform the free evolution, you are encoding more information about the frequency because you are very far from the origin. So Time and energy are resources for the estimation of frequency, and this will become important when we assess the new strategy, because we will compare the new strategy to the old strategy, fixing the resources that we gave to the two protocols. Um, Metrologically speaking, this estimation problem is very easy. Is a covariant problem, is a pure state problem, and the generator of this shift in omega are just t multiplied by the number operator. So it's very easy to calculate the quantum Fisher information, which is 4 times t square. Time is a resource, and then the fluctuation of the generator. So the fluctuation of the number operator on the state you are using as a probe. And so for coherent probe, we have the Poissonian scaling. And if you have access to some form of nonlinearity, for example, second order nonlinearity, you may prepare a Gauss, a squeezed probe, and then you are increasing your precision because the scaling is different. This is the usual shot noise, and here we have the Heisenberg folklore. Now, so let me summarize what I have said so far. So, stationary measurement bad because of this dependence on frequency, while dynamical strategies are good because there is no longer the dependence on frequency. Time is a resource, and among the possible dynamical strategy, if you have access to nonlinearity, that's good. So this would be the recipe. And is that all there is? Of course not. Otherwise, this talk would be too short. And what I would like to illustrate is an idea we were developing last year is, well, suppose we have access to higher nonlinearity, kind of nonlinearity. So we may try to encode the frequency instead of using just the free evolution plus something. Here is interaction, some interaction with a nonlinear media. And why we hope that this is more convenient? Well, because if this Hamiltonian is not commuting with the number operator, with the free evolution, we expect the information about the frequency to be scrambled across the Hilbert space to affect more coefficient in the expansion of the continuous variable state. So we believe that we have the intuition that this could be more convenient. And I anticipate that on paper, this is good for any frequency. But of course, since I'm going to invoke some nonlinearity, third order, fourth order, I anticipate that this will be of interest, especially for superconducting platform, where those kind of nonlinearities are available. While in optics, those kind of nonlinearities are very difficult to obtain. And so frequency of the order of gigahertz, which are typical in superconducting platform. And in this sense, my talk today is complementary to the talk I gave last year in Olomouc, which was about another strategy to estimate frequency. Was about well, you have some unknown frequency, you perform a sudden jump in frequency, then you leave, evolve, and then back to the original frequency, which is unknown. And this is produced in squeezing and make the frequency, the estimation of frequency more precise. And that proposal is more suitable for frequency in the order of kilohertz because you have to implement a jump in frequency, and this can be done by acousto-optical modulator in optomechanics, while again in optics this may be difficult. But on papers, this is true. Both proposals are suitable for any frequency, even radio frequency. Okay, and so finally, I'm at the core of my talk, but I have 16 minutes, so plenty of time. So this is we have an initially prepared state, and we stay simple. We assume to have a coherent probe, which is easy to prepare. Then we leave the coherent probe to interact with, to evolve, let me say, with this Hamiltonian. So free Hamiltonian, and this is the nonlinear Hamiltonian I would like to use to scramble information across the Hilbert space. And we were quite general. We we considered this and we call this polynomial case. Uh, for s equal to 3, you can call the magic gate, and this of course is generalized squeezing because of the resemblance with the squeezing, and then we have the generalized curve. And I anticipate that I will present the result for the first two cases, while the third one is not providing much improvement. And you know already why, because this is more or less commuting with the number operator, yeah, while the others are scrambling information across the Hilbert space. And then after the interaction, we have repeated preparation, repeated interaction, and then we hope that the quantum Fisher information here is larger than the quantum information we may achieve by free evolving a coherent state. So, so we will be interested in this ratio, the quantum Fisher information of the new strategy divided by the quantum Fisher information of the simple strategy with a coherent probe. And in order to provide a fair comparison, we have to give them the same time, the same amount of time, and the same amount of energy. The same amount of time is easy. Just put the evolution time equal. And in order to ensure that they have a disposal the same amount of energy, we have to impose this equality. I mean, this is the alpha we are using in the new strategy, and then we give a bit more energy to the old strategy in order to match, because the free evolution is passive, while if you ask for nonlinearities, then they are active. They are adding energy to your system. And so we impose this, and so the final expression of this ratio is this one, and we wanted this to be larger than one in order to gain something. And again, some consideration. We would like to provide a fair comparison, also taking into account practical consideration. And so we restricted ourselves to this range of parameters. I mean, beta is the nonlinear coupling, and we try to stay with beta t smaller than 1, because we performed our calculation assuming pure states, because we would like to discriminate what is due to nonlinearity and what is not due to nonlinearity. We didn't want to take into account noise, but of course, if you avoid taking into account noise, you should stay with short time. So this is to make the analysis reasonable. Then with coupling, I mean, in superconducting platforms, you have nonlinearities, but yet they are not so big. So it's reasonable to stay with coupling. And then as an initial platform, we stay this because we took this from the usual number they have in superconducting platforms. And so S1 and 2, they are not interesting. Because basically you are shifting, you are displacing an harmonic oscillator, or you are back to squeezing. So I'm not presenting a result for S equal to 1 and 2. And let me start with the genuine nonlinearities. And here are the result. Notice that the scales are very different. And this is the polynomial scale and the generalized squeezing. So if you have enough time and enough nonlinearity, then you gain something. And you may even gain a lot. There is a reasonable large range of parameters where you gain a lot. And in order to see how this is depending on the amplitude, we also consider another figure of merit. So fixing basically the nonlinear coupling, then we were optimizing. Fixing the evolution time, we were optimizing over the nonlinear coupling in order to see the behavior as a function of the initial energy. the initial amplitude. And I mean, the only information which is relevant here that it is superlinear actually is super quadratic, meaning that is not only matter of energy, is really due to the spreading of information due to the nonlinearities. And well, let me try to understand better this behavior. I mean, we were guided by the intuition that the more those nonlinearity are scrambling information, meaning they are not commuting with the number operator, the more they are effective. So we try to make a quantitative assessment of this intuition, taking into account one of those quantities that are used to quantifying non-commutativity. And so we calculate how much the number operator is not commuting with the final state. And here are the result. And can you see they are not equal? And because the skew information, the Wigner-Yanase information would correspond to a pure shift problem, but nevertheless, they are providing a guideline. If you have another problem, then you may rely on the Wigner-Yanase skew information in order to choose your parameter in order to improve estimation. And well, then one may ask, well, your analysis was referring to the quantum Fisher information. So you gain. In principle, there is much more information at the end if you apply your strategy than in the usual strategy. But are you able to extract this information with a feasible measurement? And well, we started with the simplest measurement we can imagine in this framework, which is a heterodyne measurement, the projection of a coherent state here. And we calculate the Fisher information of the heterodyne and to see how this is behaving against the quantum Fisher information. So the red curve, the ratio between the Fisher information of heterodyne detection and the quantum Fisher information. And can you see is a reasonable fraction. It's going down just in the region where the quantum Fisher information is going up. We were quite annoyed by this. And nevertheless, you can see there are several situations in which, let me take this one because it's the best one. And so can you see here, for this coupling, now this amount of coupling, the Fisher information is just 10% of the quantum Fisher information. But the quantum Fisher information was 80 times the quantum Fisher information of the free evolution. So you still gain a factor 10 using heterodyne detection and the nonlinear scrambling compared to the free evolution strategy. So closer to the quantum Fisher information. Then, of course, one may think, well, give more time to your strategy, you will gain. But in that case, we have to see the trade-off between the larger times to encode information and the degrading effect of noise. So there will be some optimal time at some point, and we would like to see whether this optimal time is larger than the times we were considering or not. And then, of course, it would be nice to find systems where the coupling is at least proportional to omega, because in that case, the quantum Fisher information can be calculated analytically. Why we had to resort to numerics, because no Bacher-Hausdorff or Dyson expansion or Magnus expansion was available to calculate exactly the evolution and the final state. And of course, related to the previous point, can strong coupling overcome noise, making the full power of time available to this? With this, I would like to thank my collaborators, Sara Dornetti and Alessandro Ferraro from the University of Milan, and Victor Montenegro from Khalifa University in Abu Dhabi. And thank you very much for your attention.
Thank you very much. Very cool talk. We have some questions.
So thank you for the very interesting talk. You mentioned that the gain of the quantum Fisher information is strongly associated, at least numerically, is associated with the non-commutativeness of the initial Hamiltonian with the scrambling. I was just wondering if it's possible to derive some bounds on the potential attainable gain of these things, potentially like using the Wigner Araki Yanase theorem, something like that, to derive some some bounds on the possible
Wow.
gain, something like that.
Thank you very much. That's very clever, and I'm very envious to not having thought this before you. Yeah, no, that could be a very good idea. Yeah, thank you very much. And no, we didn't try, basically because we were sticking with specific form of the Hamiltonian, so we don't go to in full generality. But you are right. That should be possible.
Yeah, I think I ask this simply because I have read some papers on like how the quantitative these the gains of the quantum Fisher information is connected with the breaking symmetry breakingness or something like that.
Yep, exactly. Yeah.
Thanks.
Yeah, thanks. So I have a simple question on your heterodyne measurement. So what is the definition of your local oscillator? Is that just a perfect sine wave and you measure for delta t? Or is the local oscillator kind of has a temporal shape? Or could you also temporally shape it? That's kind of to understand what the heterodyning really is.
No, we decide, but I mean, I'm not doing homodyne. I'm not measuring a single quadrature, but two quadratures jointly. So I'm accepting the 3 dB of noise. So you're asking for implementation. Well, it really depends on the kind of modes you are dealing. I mean, in superconducting platform, I'm afraid they are doing some kind of photo counting to achieve the heterodyne. So yeah, your answer is there.
More questions? Yep, there's one at the back.
Like, do you have an idea like how is the information being scrambled? Like, in the sense, like for example, what happens in phase space? What kind of features? Like the Wigner function of the state after the evolution or whatever. Like, why is it giving good results in a way? Is the question.
Why it's giving good result? Well, the idea is that I mean, free evolution is just changing. Now let's abandon the phase space and move to the Fock space. The the free evolution is just adding a phase to each Fock coefficient. So the amplitude is fixed, you're just adding. And so that's the encoding information. And then you maximize over all possible measurement and you have the quantum Fisher information. Now, this Hamiltonian, the nonlinear Hamiltonian, is changing also the amplitude in a very messy way. And so since it's changing a lot, tiny variation of the frequencies are changing more coefficient. And when you maximize over all the possible measurement, likely you get a better precision. It's just, you would like your encoding Hamiltonian to create a mess in the Hilbert space, because this is the sign of a better encoding, or at least is the pre-requirement to possibly have an optimized readout which is able to exploit the mess you are creating with the Hamiltonian.
There's one more question.
Thank you for the great talk. So I have a quick question about the nonlinearity. So I was wondering, how would you like to control, do you need precise control over those nonlinearity, or if they're there and they could help with your measurements? Thank you.
Well, the only assumption that we made is that they exist and they are constant during evolution. So this is the only requirement. So control in the sense they are there for the entire duration of the evolution, which is, it is an assumption. I know, but it's the simplest assumption we could make.
So let's thank Matteo again.